Yeah, I just need a chalk a little bit. Yeah, I guess I'll use these ones. Okay, yeah, I'm ready.
Okay. Very happy to have Yanki to visit us from UK. Tell us about the non-relative resolution using your symmetry of some surface. Singularity. No, versal.
I am not sure. Yeah, that's yeah.
We'll tell you what you'll talk
That was very different. Than, I can tell you about that if you like. But so okay, so thank you for the invitation. So I had a little bit too much coffee, so I might go fast. So please slow me down. So if things don't make sense, please ask questions. And I understand this is for 2 hours, right?
Yeah.
So that's great. So we can kind of chill and talk about questions in more detail. So, right, so here is a, so let me try to set this up as a story, right? So, so we have X, which is a, let's say, a smooth projective variety. And so from X, you can, so over C, today always over C. And, you know, there's this category called coherent sheaves, category of coherent sheaves. It's an abelian category. And that's not very different than X, right? So it's essentially equivalent data. But then there is the derived category of coherent sheaves. And now we did something drastic. So on one side, we lost some information. You can't recover X necessarily. On the other side, we got some more symmetry. So this is a good thing to do. So somehow it's get some interesting information about X that's manageable.
Do you think you can't recover X?
Not in general, yeah. Not in general, yeah. There are some cases where you can. But
you mean is it known that you can't?
Yeah, like there's Fourier-Mukai transforms between flops and so on, for example. Yeah, there's a, you can't in general. But it is a, you know, this is kind of a, you divide out, this is more homotopical nature. So, right, but then how do you study this, this category? Well, when X is smooth and projective, you know, sometimes, not always, but sometimes you can find an exceptional collection. So sometimes.
So we can recover complex structure of X or not X?
No, you can't recover even complex structure of X sometimes.
In general?
In general, yeah. Right, but so how do we study such a thing? Sometimes we can find an exceptional collection, right? So exceptional collection is some, you said you like A side better. Exceptional collection is the analog of Thimble's, right? So it's kind of some collection such that X of EI is just in is just in degree 0, and it's just given by the ground field. And then there is also some direction to, if there is a morphism between I and J, there is a direction, right? Of course, the first example of this is the derived category of P1, right? So this is a well known that it's the same as the derived category of this quiver, right? So you have a structure sheaf and O1, for example. So what do we have here? We have some sheaves, so some objects, and they generate this category. So anything else can be obtained from these guys, and they are very simple in the sense that the endomorphism algebra of these guys is just this quiver. It's a 4-dimensional algebra. So in some sense, the derived category of this thing has been reduced to pure representation theory of this finite-dimensional algebra. So, and in general, when you have an exceptional collection, so if you have an exceptional collection, you can think of it as gluing of categories of very simple nature. So each object just generates a category of complexes over your ground field. So I said today we are C, right? So this just by itself is just the derived category of C, which is just of the field. So it's just complexes over this field, and then they are glued together by these maps between them. But so if you want to approximate, get some approximate information, you can forget about these arrows and just look at these pieces, right? If you have an exceptional collection, you're kind of done at this point. You just have a bunch of these very simple categories. So of course that's not achievable in general. So so what you can do is in general, the next. It's very heavy. Huh? Okay. Oh yeah, this is a physics department. Yeah. So. So dBx. So the next thing that you can hope for is a SOD, so semi-orthogonal decomposition, and that's basically the same kind of story, but the pieces are more non-trivial. Okay, so the category is decomposed into pieces. So these RIs are some finite-dimensional algebra, say. Okay. And so there's the derived category of that algebra. That's one piece. And there's maps from this to this category or anything on this direction, right? And so that's what we call an SOD. So it decomposed in some kind of triangular fashion, right? So there's no maps from these categories to the back. Question?
So you give an example for RI or finite-dimensional algebra.
It doesn't have to be, yeah, fine. It's just an example, yeah. Yeah, in general, you might be having several categories, and you can have a decomposition, and you forget about how they glue together, and then focus on pieces and try to understand those pieces.
Yeah. How about if you actually want to know exactly how they glue together?
Right. If you want the whole information, which is very hard to get in general, you want to know each categories and how they're glued together. Yeah, but that's very rarely achievable.
Are there examples where it happens?
Here, there are many examples, but yeah, if I give you a random X, even finding the pieces is hard. Whether it admits an SOD is hard. Yeah.
So the example where it's known is just exceptional collections, or there?
No, we'll come to that. Yeah. So I'll soon give some example of a SOD. So should I give you one now? Yeah, I can give you one now. Maybe. Here's a example of an SOD. So if I take derived category of P112, so it's a weighted projective space, but not a stack, just a singular space. This has an SOD of the following form. It doesn't have an exceptional collection. The reason that I chose this example is exceptional collection. Having an exceptional collection implies that your X is smooth. Okay, so did I say that correctly? Yeah, I think that's well. Anyway, so this one is not smooth, so I don't expect to have a exceptional collection. But here's a decomposition, SOD. Okay, so there is objects. These are generated by some line bundles here, but this is generated by some more complicated vector bundle. And there's an SOD this way, and the endomorphism of this vector bundle is this algebra rather than K. Okay, so that's we'll get to this kind of examples more. So I'll give you more information in a minute. So okay. Sorry. Yeah. Yeah. Okay. So next, yeah, I want to discuss what do we do when X is not smooth. So
Maybe you can tell us the actual subcategory of this.
three what components?
Yeah, which subcategory?
Yeah, I will tell you in a minute. Yeah. Okay. You want the objects, right? I'll tell you because I'll tell you more general thing. So if here's another thing that you can do more generally. Maybe you don't have a SOD, but sorry, you don't have this nice description in terms of derived categories of algebras. But here is something that you might hope to have. It's called Kawamata SOD, and it asks you to find an SOD of the following form. So you have derived category of some algebras, and then there is a remaining piece, and this remaining piece is a subcategory of the perfect complexes. So let's discuss what this means. So when X is singular, there are two different categories. One is a derived category of X, and the other one is perfect category of X. So derived category of X is objects are complexes of coherent sheaves, and perfect modules is complexes of vector bundles. Okay, so these are the same if and only if X is smooth, but in general they are not the same. Okay. Huh? Yeah, bounded. Yeah, and one way people study these things is they take a quotient, and they call it derived category or singular derived category, or sometimes matrix factorizations. And somehow this category measures how how singular X is. Okay. But here it's a bit more ambitious. You don't take a quotient, but you try to find an SOD such that you absorb. So this is a absorption of singularities. So the singular part, sheaves coming associated to the singular part of X contribute to this part of SOD, and then the remaining part is perfect. Okay, categories of vector bundles.
What does this look like for just?
Yeah, the first example is coming. Yeah, the first example is coming. So yeah, so this is called Kawamata SOD, and the name absorption of singularities is, I think, due to Kuznetsov and Schindler. And I'll give you the first example now. So here it is. So I have a P1 and another P1, and they intersect transversely. And I want to give you a SOD associated with this. And it looks like as follows. So there's two pieces, A and B. And B is in perf. Okay, so and A is the derived category of some algebra. So, and then in this case, it will be derived category of the following algebra. And then B is just the derived category of the field. So there is an exceptional object, and B, you can take any line bundle. And on the other hand, there's other objects, two other objects, that give you whose endomorphism algebra is this finite-dimensional algebra, and that's associated to this node. So let's work out this example in a bit more detail. So, so the A is the how should I say it? So A is generated by the following, and they are generated by O of, let me call this copy C1, this copy C2, O of C1 and O of C2, okay? And B is, in this case, generated by O of 1, 1, the line bundle of 1, 1. So these are the structure sheaves of these, this P1, right? So it is very much not a vector bundle. So it's kind of passes through this. So you need those two for A, and B is a line bundle. So it's a subset of, it's 1, 1 means on this P1 it has degree 1, and on this P1 it has degree 1. Is this supposed to be what, sorry?
Are P1, 1, 2 example?
No, this is two P1s. These are two curves, P1s, that intersect.
What's the total space?
That's the total space.
That is total.
So it's a curve.
Okay.
Yeah. It's a curve that intersects itself at one point, two components, which each are lines. And it's a singular variety. And the point is that its derived category has a Kawamata type SOD. So, and specifically what it means is that there is no homes from this guy to these guys, right? That's what it means. So.
Is there some procedure in which we can interpret the result, like the right-hand side, as a gluing together of individual two arrow quivers, how do we call it, valence or right? Because
so this is a different quiver than the valence one. They go the opposite direction.
Yeah, it is a different. Yeah. This one is like, so the specifics of this specific quiver is like focusing on the node.
That's right.
Versus focusing on the what is remaining.
That's right.
But like I've been wondering for many years, like how much of mirror symmetry, how much of categories, and so on can we glue together from pieces? For example, since we already have an equivalent for P1, is there any procedure where you can compute the draft category of this coordinate crossing from two?
Yeah, I mean there are many ways you can compute it. Yeah, you can glue, but I mean that's not what I'm focusing on, right? So what I'm talking about is because there's a singularity here, there is an associated category, kind of seeing that singularity, and then that's a piece of our total category. The rest is generated by some vector bundles, and there's an SOD, right? So that's this notion of categorical absorption. It's very new notion, but the idea is to whenever you have a singular variety, you try to find sheaves responsible of that singularity, and then the rest is as if it's smooth, right? So let me just now give an A model version of this. So maybe that'll help some other people. So for this two P1s intersecting at a point, we have a mirror, right? So here is the mirror. So that category is the following partially wrapped category. So it's the three-punctured sphere with two stops. Okay, so that's the partial wrapped category of this one is equivalent to this one. So this is an example of mirror symmetry. And the objects that we have are, so this is the these are the objects that are mirrored to these OC1s, and so the morphisms are given by these chords, right? And then the mirror to O11. So maybe I'll use this these colors here. And mirror to this line model O11 is the following Lagrangian. Okay, and you can see that this, these objects generate because they cut the surface into pieces. But also you can see that there is no morphism from the blue to the purple. All right, so that's the key property.
Can you help us understand how from the geometry here? You're telling us, but I actually maybe I don't understand the B cipher. But what is this?
You can draw the P1 plus side by side.
So that two P1, can I think of them as meeting a torus invariant point? I see. So just two P1s attached.
Yeah. So the mirror is like
at a torus invariant point. Okay.
Yeah.
Not at some generic point.
I mean, I can just tell you it's xy equals to 0
I mean, it's actually important, right?
in
Because
P2,
no
right?
I have to tell you how they meet.
Of course, yeah. This is it.
Okay, good.
In P2, right? It's two lines intersecting at one point. So I.
Of course it matters, but is it very
Right. So it's just it's the simplest singularity that we can come up with, right? There's no other singularity that's simpler. So, and this is about the decomposition of Dirac carriers of singular spaces. So we need something singular. But yeah, the point is that this category decomposes into two pieces, A and B, and there's only morphisms from A to B, but not the other way around, right? So. Sorry, I didn't. No, this is just a high. The surface. This curve is just defined as the hypersurface. So its singularity is at the origin. I don't think there's any matrix factorizations here. I just wrote a formula to tell you what the what the curves. These two curves intersect at one point. Yeah. Whenever two varieties intersect, right, the intersection is singular.
I see. So I would have just drawn that picture. I would have drawn it as so the
like this.
The outer boundary, the homological form is dz, right? Not dz over d.
That's right. Yeah. Yeah, I drew it this way because it's planar, so I can.
Okay. Right. No.
Yeah. Huh? Yeah, I mean, anyway.
No, but also the other one is better for you guys.
Yeah, I mean, it's. I'm happy to clarify. Yeah, it's fine. Yeah, thanks for questions. Yeah, that's what I should have said. Yeah, I have no problem with questions. Yeah. So, okay. And that's an SOD, and it's the first example of our categorical absorption. Now, the next thing I want to say is, yeah.
So you choose some like the projective instead of some more local one.
Yeah. I guess, yeah, I mean, there is no SOD for the local one in this case. So this example, yeah. So, yeah, I mean, this categorical absorption story makes a bit more sense in the projective setting because you want like this to be a finite-dimensional algebra. But you can ask, yeah, I guess you can ask it for open things too. So.
I also ask for free. Sorry, this is my defect as a B-side person, but how do I see that the purples are going to have the correct
Okay, good question. So you want to see why this is this? Right, good. So there is a little detail there, which I want to avoid, but let's discuss it since you asked. So um, um, so it's not the endomorphism algebra of this thing is this algebra, because I'm not taking perf here. I'm taking derived category of this, right? So if you want to get this algebra, you have to find the dual objects to this, and those are the following. Those are the following, this and this. And the endomorphism algebra of this one is this algebra, okay? And these guys, how do you see that? That's that algebra. So A would be this wrapping, and then B would be this wrapping. And in terms of the A side, the B side picture, those green ones are the following line bundles. Yeah, so this is a right. So in terms of representation theory, this is some kind of projectives versus simples business. So, and because I want a finite dimensional algebra, right? The finite dimensional algebra, this means the modules which are home finite with respect to this, finite dimensional modules of this algebra. So, so it's not the endomorphism algebra of these generators. Yeah. Yeah. Okay. Now I'm getting a sense of what people know better. So, because in some other crowds, this would take half an hour to explain. So right. So yeah. So this algebra is for these ones. And if you want to write OC1, the endomorphism algebra of this guy, it will be the Koszul dual algebra. So it would be like A and B, and then the relations will be well, there is no relations. So it's going to be A, B, and so on. Right. So that will be the endomorphism algebra of these generators. Yeah. Okay. Good. Just to mention some names. So more generally, if you have any genus zero curve, which kind of has like it's a tree of P1s, there is a categorical absorption that's a result of Bourbon. So, and then this is pretty much it in the case of curves. Okay, so next I want to do, maybe I want to do one more example. Well, I want to do, sorry, one more. Another thing that you can do is the following. So let's put this singular thing in a family. Okay, so we have a CA1, and the special fiber is this P1, P1. So this is our curve C, right? So let's call this C. And general fiber is just a smoothing of this, right? So it's just a P1, right? So this this kind of decomposition, it's a theorem. It's not a hard theorem that if you deform in a flat family, you preserve, you get a decomposition again. So that now this is a family. Yeah, C is this thing. C is this thing. This whole thing, right? Yeah, this thing. I'm just giving this example. And this decomposition. So now there's a family, right? This family of this dbx also has, so each side, each of the categories get deformed, and then the property of being SOD gets preserved. Okay? So, and what happens is just these algebras get deformed. So there's nothing that you can deform here. It's just a K, but this one gets deformed, right? And what happens is it becomes the following. Oh. So this one becomes A and B. And now instead of having 0, it will be AB is T times identity of the second object, and BA is T times the identity of the first object. Okay, so that's the so we get this A is the Dirac category of this one. Okay. So that's what happens, and well, what's this algebra? Something very simple. It's if T is not equal to 0, so let's say T is equal to 1, what's this algebra? So it's a 4-dimensional algebra with the relations AB is E2 and BA is E1. E1 and E2 are idempotents. Yeah, what is it? I mean, it's something that you learn in, that's right. So it's the 2x2 matrices, all right? So E1 is this one, E2 is this one, A is this one, and B is this one.
Really nice to draw that cylinder under.
That's right. So that's the relative Fukaya category. So if you take the relative Fukaya category, let's draw it this way now. That gives you A. Okay. So, right. So, but let me just point out one thing here. What happened here is I have a family of algebras. Let's forget about B. B is kind of simple. It's just, a single line bundle. It has degree 2 here and here degree 1, degree 1. But this one, what happened is this one was this. Well, I don't know. So it was these guys, and now when you deform, they turned into a new. They turned into two objects which are isomorphic, right? Because A and B, this matrix algebra gives you the isomorphism between them. So it became the sum of two things, right? So which is so let's think about it as follows. So I want to introduce the notion of an order with this example. So outside of this T, I have a 2x2 matrices. But at 0, I have this algebra A, B, BA are the relations. So it's a flat family of algebras, 4-dimensional algebras. General fiber is 2x2 matrices, and special fiber is this more complicated algebra. Yeah. So, and that's what's called an order. So it's an order, matrix order. And one way to think about matrix orders is the following. So you fix the dimension, for example, 4 in this case. So on a 4-dimensional vector space, you look at the moduli of all algebras, all associative algebras. Okay, so that's some space. And this is kind of a line in that space. Huh? Yeah, let's imagine there is some space. So this is a 4-dimensional associative algebras. Okay, so matrix algebras is one example, and this is another one, right? And so you can think of this as a space as follows. So you have some bases, right? So you have 4 basis elements. I don't know, x1, e1, x2. So a general element is like this, right? And then you require that associativity holds, right? So there's some quadratic equations. So that's some huge dimensional singularity, right? And the change of basis is acts on this. So it's a space with a GL for action, right? So, and in this space, there's different components. In fact, for 4-dimensional, it's classified. There's 5 components. It's a theorem of Gabriel. So if you encounter 4-dimensional algebra, you can look at this paper. Right? So there's 5 components. And one component has the matrix algebras. So all the matrices in it. And but it's still that's an open set, and this is kind of some disk in it, right? So it's kind of like some disk. So here we have M22, but here we this point is this algebra. Okay, so that's what's called an order. Yes, for 4 it's known. For 5, I think it's also classified. Afterwards, it becomes intractable. So, but the notion of order, I just wanted to give you an idea about what the definition of order is. The definition of order is some degeneration of matrix algebras, but in the center, it's more interesting algebra. Is that okay? Right. Okay. All right, so that's what an order is. And now I want to go to the next dimension. Yeah.
Remember some of the paper you introduced vector P in the base and you write vector matrix in a uniform way.
In a uniform way. Yeah, maybe. So let me write this this algebra. I can write it as follows. So is that what you mean? Let me just write it. So this is a subset of M2 by 2 matrices of CT. So polynomials, entries are polynomials in T with C coefficients, right? So if I didn't put a T here, it would just be a flat 2 by 2 matrices everywhere, right? I put a T here. This is a subring of this, which is an order. So if I invert T, it would be 2 by 2 matrices. But if I don't invert T, it becomes that algebra. Is that what you were asking? Yeah. So yeah, you can always embed an order into matrices with polynomial entries like this. Yeah. So this is an example of an order. Yeah, it's I read a little bit about the literature on orders. It was kind of very active on around 60s or so. Now, if you go to anyone and ask what an order is, it's not very common knowledge. It's but it's a very it's a very reasonable notion, right? So it's like a globalization of matrices. Like that's a reasonable way to think about it. When you have an algebraic variety, right? You have a sheaf of functions, right? So you have a variety. So everywhere there is some commutative ring, right? And you can imagine it, you have a space, and everywhere there's matrices, right? So there's a sheaf of algebras, and everywhere there's matrices. And there is some loci where this sheaf of algebra, this matrices degenerate, right? So that's what an order is. So that's very reasonable. As long as you think of matrices as reasonable, that's reasonable. Right? So that's and they have derived categories and everything. Yeah. Okay, so now I want to go to so let's see. I want to go to an affine. So I want to get to some surfaces. So here is a so X is now the following. It's a toric singularity. So there's a notation for this. Algebraic geometries write it like this. What is this? So R and A are numbers, okay, and they are relatively prime. They are relatively prime, and mu R is the cyclic group of order R that acts on C2, right? And so psi is the Rth root of unity, and it acts on xy as psi x, psi to the ay. So that's a toric surface singularity. All toric surface singularities are like this. Okay? So, yeah, I find this notation very funny, but this is what they write. This means the space. So 1 over on 1a. So it's very standard notation. Yeah. So and this space has this coordinate axis, x equals to 0 and y equals to 0, right? And then there is a singularity here, which is this quotient singularity. When a is equal to r minus 1, this is the a r minus 1 singularity, okay? But otherwise, it's a more complicated singularity. So, okay, so I projectivize this because as you pointed out, I like projective things more in this talk. So, and I projected these lines as well into a divisor like this. So this is x bar, a projective surface, which is a compactification of x, and I kind of so it's singular here again. So this is the singularity. This is this 1 over 1a over r singularity, right? This is a smooth point, but the divisor intersects itself here. So this is a smooth point of x bar.
X bar is like the root
Huh?
P1 cross P1.
So not necessarily. I mean, it's just some compactification of x. It can be different. It's just a projective surface that includes x as a open affine, and it's smooth everywhere else other than this. And I need just a couple of technical conditions. I want it to be. I want this cohomology to vanish. And I'll explain why. So I want it to be kind of rational. And I want its deformation theory to be the same as the deformation theory of this one. So, and yeah, there are many of x bars, okay? So there is no canonical choice. It's just embed x into x bar with these conditions. I don't know, like P114, for example, would be a good x bar for R for A equals to 1. Right, so that would be a good example of an X bar. So, but you know, I don't really need what happens in X bar other than these conditions. And the reason that I ask this condition is eventually I will study deformations of this singularity. So this affine singularity, right? So this cyclic quotient surface singularity. And what I want is that the projective surface has the same deformation theory, right? So there's no local to global obstruction. So whatever, if I can deform this one, I can deform the corresponding X bar as well. And that's this vanishing condition. Okay. So it's a kind of a technical thing to work with projective things.
There are abstract reasons for adding an X bar to exist such that they have the same information.
Yeah, I mean, it's you can easily construct it. Yeah, just starting from some blowing up and so on. Yeah.
Like it's partial normalization.
Of what?
Of x.
Well, x is fine.
X, yeah, sorry, it's normal. Like, I see. Okay. May I ask when we're talking deformation theory, we are talking commutative deformation.
Right, but not yet. Yeah, but yeah, it will be a while until I get the deformation theory. Yeah, but yeah, I'm talking about just deformations of algebraic varieties. Yeah. Okay. Right. So now I claim that x bar. So x bar has a nice categorical absorption. Has a Kawamata SOD. Okay. So, and the point is we want to absorb this singularity, this cyclic quotient surface singularity. So the point is I want to find the decomposition of dB x bar into dB of R and some other component B, and this B is in the perf of x bar. Okay, so that's what I want to describe next. So, you know, we saw this curve example. This is one dimension higher and more complicated singularity. And this R is, so this is a result due to Kawamata. So you guys know this guy, right? It's a very famous Kawamata. So it's kind of, huh?
Resolution of singularities.
No, that's Hironaka.
Yeah, I mean, yeah. But like minimal models here.
Yeah. So it's yeah. Anyway. So, and the point is he constructed a vector bundle on X bar, and such that that vector bundle kind of captures the singularities, and then there's a orthogonal SOD part, and this part is in perf. So I want to describe this vector bundle. And it goes as follows. So it's really cool because, you know, X bar is singular, and but this is still a vector bundle on it. Okay? And how does this vector bundle come about? So I'm going to describe a vector bundle which kind of lives here. Its Koszul dual will generate this part. Okay, so that's another way to say it. So B is a bunch of exceptional objects, generally. So it's just some line bundles. B is less interesting part of the story. Okay, so the singularity is here. And B kind of depends on how X bar is. The B depends on the details of X bar. Whereas this one is about the cyclic singularity. Yeah, I will. Now I will construct this vector. Yeah. I mean, here it is. So remember, this X bar has this divisor E, and this E is sorry, maybe I forgot to say E is an anticanonical divisor. Okay, so E is a zeroth set of an so E is anticanonical divisor. Okay. What did I want to say? Yeah, so it has these components A and B. So this point is the singular point, and I want to capture that singularity. I consider the ideal sheaf. It's the ideal sheaf. Or so what happens is this because this is singular, this A is a divisor. It's a Weil divisor, but it's not a Cartier divisor. Okay, so it's a it's a curve. It's a divisor, but it's not cut out as a zero set of a section of a line model, because you can't do that when you can't always do that when your variety is singular. So A and B are just these coordinate axes, right? So when in the local, huh? Yeah, before you take the quotient, it was coordinates.
What is it?
E is when you compactify, what happens to that coordinate axis? So the coordinate axis is kind of like like this, right? But when I compactify in such a way that it's like this.
E is the intersection of the two lines, or?
So they intersect here.
I mean the second intersection.
The second intersection, E is the whole thing, the curve. And I compactify X in a way that the anticanonical looks like this.
E is the anticanonical.
Yeah, E is the anticanonical.
So that it has some, like, locally it looks like a B and B.
A and B are components of anticanonical. So this is a projective surface. Inside there's an anticanonical divisor, and the anticanonical divisor has two components, A and B. And these components pass through the singular point. Mm-hmm. Okay. Sorry? I constructed that way. Yeah. So in the open thing, it's clearly anticanonical, but yeah. So I construct compactification that way. So right. So I take this all my and this there's some choices here how they intersect. There might be different ones. I just picked one, so this is convenient. So right. So this is an ideal sheaf. So it's very much in the coherent category, like it's a coherent sheaf, but it's not in the perf. Okay. So and this side of the category is generated by this one. Okay. But I don't take endomorphisms of this one, because endomorphisms of this one will be infinite dimensional, right? So this is kind of like goes through the singularity. It's not a vector bundle. It will be infinite dimensional. Okay, but there's a dual object, which is the vector bundle. That's what Kawamata constructs, starting from this, and he uses the following construction. So here's an algorithm. So you set. So you're given. So this is RG. You set F to be G. Okay, and then you look at is x1 of f and g 0? Okay, is there an extension between f and g? And if no, then we are done. And stop. Output f. Okay, if there is an extension, then you construct the extension. Wait,
R is yes or no, or swap put it up. So if x is 0, then we already stop. Or is it?
If x is 0, we stop. If x is
maybe that's swap.
Oh yeah. Yeah, if is x, yeah, that's right. So maybe I should say no here and yes here. You found a gap in my algorithm. Right? So if there is no extension, no, if there is whatever. Okay, so you construct a non-split extension, if you can. And then you set f is equal to h, and then you go back. Okay? So this is called the universal extension, maximal iterated universal extension, maximal extension of G by itself. Okay, and usually this doesn't stop, so you don't get anything. Okay? But if it stops, you get something unique, and it doesn't depend on the choices. Okay, and Kawamata applies it to this O minus A and gets his, as a result of this, he gets a vector bundle. Okay? So that's the Kawamata. So output of the algorithm is a vector bundle F, which is a rank R vector bundle. So this is called the Kawamata vector bundle. It's kind of a very peculiar object on this singular projective surface. So is this procedure okay? Yeah. Okay. So there are some very nice properties of this vector bundle. One is, so essentially by construction, it doesn't have any extensions anymore. Right? If it did, we would continue. And moreover, as a bonus, we also get x2 is 0. Yeah.
So you're saying this ideal shift, the homomorphism of this is going to be
That's right.
singular.
Mm-hmm.
And is there some object in the static version that is
I don't know what that means. The stacky is a resolution. Yes. So there is one object there that descends to F, but not to O of minus A, because push forward, you can only do in vector bundles, right? So in covariant sheaves, you can't usually. So yeah, I don't think so. But yeah, I don't know. So yeah, but we will come to the resolution in a minute. So this vector bundle has this very nice properties. Okay, so first of all, it has no extensions. So it's on a surface. The only thing that's left is the endomorphism algebra, and that's R. Okay, so and this R is called Kalck-Karmazyn algebra. Yeah, unfortunately, there's a lot of K's in this business, which is not a good thing these days. So.
another question is that is this algorithm give you a unique output? Just give you some maximum.
Yes, it gives you a unique output. If it stops, it gives you a unique output, and it doesn't depend on choices. Yeah. So, all right. So we get this R, and yeah. So we have this decomposition, and we want to understand what this R is. R is a finite-dimensional algebra. This is a finite-dimensional algebra. Okay, and I'll tell you what this algebra is. So it's the Kalck-Karmazyn algebra. So so that's a very nice thing about. Yeah. We start with this singular O minus A. So this is a shift. Right. So I have this singular projective surface, and this is the singular point, and I take an ideal sheaf through this point. Okay, so it's this O minus A. So it's some sheaf that only exists because there's some singularity, and this kind of it's about that singularity. I take that guy, and that guy is that guy is the generator of this side. Okay, so this side is the generator of that.
And you will calculate B for it?
Huh?
You will calculate who generates B?
No, B I didn't care that much right now. B is kind of simple. It's a bunch of line bundles. It depends on the X bar. But what I'm calculating is this R. This R is a finite-dimensional algebra. So this G generates a category, but it's actually the category of modules on a finite-dimensional algebra, which is the dual. It's the endomorphism algebra of the dual object, and the dual object is this F, the result of the algorithm, and it's also a very nice thing, which is a vector bundle. It's not a complex of any. It's just really a vector bundle. Okay.
So you're clearing up the ext f to g.
Say it again.
You're clearing up the ext1 f to g using this Karmazyn, and it's a theorem saying f itself will have this nice property.
Yeah, so you start from G and you kind of remove all of its extensions. You try to extend it by itself, until you can't extend it anymore. So, and then you get F. Okay. And now, let me describe what R is. R is this beautiful algebra. So R is a finite-dimensional algebra, and it was computed by these guys. So somehow, abstractly, it was known as exists, this decomposition, but computation of this R was a bit involved. And you'll see why. It's kind of funny algebra. It's a finite-dimensional algebra. Huh?
For specific R and A?
Yeah, for each R and A, there is an R. Okay?
But it's always finite-dimensional.
It's finite-dimensional algebra. Yeah, I'll tell you what it is now.
Five or
Finite.
finite.
What's 5?
I thought it was 5-dimensional.
Yeah. Okay. So here's a brew, Jung continued fraction extension. So this is something that you teach the undergrads if you have good undergrads.
What's the first name of the principle?
Here is a brew. Yeah. So, and it's the following. So you take this number, this rational number, and you do this. Okay? And it goes up to 1 over CS, and each CI is greater or equal to 2. Okay? So yeah, I'm not. So I'll do 7 over 4. 2 minus 1 over 4. Okay. Right? And so so this algebra has a description as follows. So it's RA is C freely generated by S variables, non-commuting variables. Okay. So S is this S. So in this case, it will be 2. What's wrong?
Whenever I see continued fraction, I see there's some magic happening.
Yeah. So and the ring. So this is it's generated by this and the following relation. So Zj to the Cj is equal to 0 for all j. Okay, so you can only take that much power. And one direction of product is 0. So it's a very, very non-commutative algebra in general. And the other direction is the relation like this. So Zj, Cj minus 1, Zj plus 1, sorry, Zj minus 1, Cj Cj minus 1 minus 2, Zk plus 1, C. It's not very important that you understand what it is exactly. I just want to give an impression of it. Is equal to 0 for all j greater than k. Okay? So these Cj's are these guys that appear in the continued fraction. So let me just do this example. No, they are it's a non-commutative algebra because it's an endomorphism algebra of a vector bundle, right? So there is no reason for it to be commutative. So it's a non-commutative finite-dimensional algebra. No, Hirzebur didn't come up with this. Is not here. Hirzebur came up with this continued fraction. Yeah. No. Huh? Yeah, I mean, the point is there's plus version and minus version. So Hirzebur is the minus one. And it's related to resolution of the cyclic singularity and self-intersections of the exceptional divisors. Yeah. So, but this algebra is this Kawamata and Kalck-Karmazyn. Yeah. So it's a non-commutative finite-dimensional algebra. So let's write it for this. I wrote that one. I will get there. So yeah, so great. Yeah, so I like the audience is very attentive. It's great. I guess the ones that are not attentive left over. So 7 over 4, 2 minus 2. So here's the algebra. Did I call it R7? 4 is K Z1, Z2. So there's 2, right? So it is generated by 2. And the relations are Z1 square, Z2 to the 4, Z1, Z2, Z1, Z2 cube, Z1. Okay, so it's a finite dimensional algebra. Yeah, next page has the basis. So the basis is 1, Z1, Z2. I mean, you can probably do this faster than me in your head. Z2 square, Z2 square, Z1, and Z2 cube. Hopefully it's rank 7. 1, 2, 3, 4, 5, 6, 7. Okay? So it's a 7-dimensional algebra. So
your R over R minus A. So your A be 3 in this case.
yeah, A is 3. Yeah, that's right. 7, 3. Great. Yeah. Yeah, that's what I meant by attentive audience. Yeah. Okay, so let's get. Yeah, I mean, maybe we are getting bored about this algebraic geometry. So let's get. Huh? So let's do some meter symmetry now. Okay, so right. So this is this finite-dimensional algebra. Okay, so firstly, I will describe a new description so that you don't have to do continued fractions. Okay, so that's a new description of this algebra. That's in our paper. What is it? So, and it's the following. So it has basis Wi, and I is an element of Z modulo R. Okay, so these are the bases of the algebra, right? Here I gave it the generators of the algebra. Now I'm just giving you the basis of the whole vector space. Okay, and I'm going to tell you the product. So Wi times Wj is either Wi plus j, so I plus j modulo R, right? Or 0. It's one of these, and I need to tell you which one. So and here's how you decide which one. So first you compute B, which is A inverse modulo R. So that's easy. So what is it for 7, 3? Come on, I need help. A is 7, sorry, A is 3, R is 7, and I want B.
A 1 over 8.
Huh? A is A inverse, yeah. Huh? 5, great, thank you. B is 5. Okay. And now I draw a grid. I'll draw a grid here. Let's see. The grid is as follows. So 0, it starts from 0, 1, 2, 3, 4, 5, 6. And then this is another 0. And then, so as I go up, I just increase by 1. Okay? And as I go here, I decrease by minus b. So minus b is 2. Right? So I have to always compute this inverse and minus and so on, whatever. So, and so that means 2, 4, 6, 1, 3, right? So 1, 3, 5. 7 is 0, so I put a dot. Okay, so 2, 4. So, sorry, just give me a second to copy this here. But it's just a grid. 3, 5, 2, 4, 6. 4, 6, 1, 3, 5, dot, and almost done. 1, 2, 4, and so on. Okay, so it's a lattice inside Z2, and then I look at this grid, and I look at so I'm supposed to find. So I start from 0, one corner of my. So I'm going to draw a rectangle in this thing. And one corner will be here, and the other corner can be anywhere. But I'm not allowed to touch these zeros. Okay, so I have to I'm kind of constrained in this region. Yeah, I guess, and I have to look at if I can fit a rectangle here. Okay, if I can fit a rectangle, that means that the product is okay. So for example, this rectangle says that W4 times W2 is W6. Huh? That's right. So I can fit a rectangle with one corner I, one corner J, and the other corner necessarily has to be I plus J. I can fit a rectangle there. If I can, then there exists this. Okay? Yeah, obviously, people who know Fukaya categories, this is a product, right? So it's a, but but you can. You put this lattice and then you define this thing. It's a finite-dimensional algebra, and it's exactly this Kalck-Karmazyn algebra. Okay.
You don't allow any dots inside, or you don't allow to cross the dots?
Yeah, I'm not allowed to cross through dots. Dots are holes. Huh? No, it's not okay. It's a hole. I can't pass through there.
So, for example, W3 times W4 would be 0.
Let me see. W3 times W4, yes, it will be 0. Where is your W3? Yeah, that will be 0. Yeah. And W0 is identity. Sorry, I should have said this. W0 is the unit of the.
Because the basis for this algebra, and we're now going to interpret it on the A side.
We're what?
We are going to interpret it on the A side.
Yeah, soon. It's coming. Yeah, it's coming. Yeah, but I just wanted to tell you, maybe you don't like continued fractions and relations, right? This is an easy way to compute it. But of course, this is coming very close to being a torus, right? So torus is coming. Okay. So, okay. Yeah, maybe I could have told you here which WI correspond to which ZI, but maybe let's skip it, yeah, and you can figure it out from all possible products. Okay, so here's the main discovery of our paper. It's this picture. So this is our picture of a torus. This is a torus. Okay, real torus T2. And here's a Lagrangian. Goes like this. One, two, three, four, five, So 1, 2, 3, 4, 5, 6, 7. Yes. 1, 2, 3, 4, 5, 6. So I need one more. And then this one is this. Okay, so this is the number of these guys is R. Okay, and the number of these guys is B. Okay, so and this is an immersed Lagrangian in the torus. Okay, so and there is two holes here. One is here and one is here. Okay, so this is a twice punctured torus and some very complicated immersed Lagrangian, which you draw this way. Okay. So, and the claim, the discovery or whatever, the progress is this is the mirror to the Kawamata vector bundle, this object. Okay. So, and I will explain in what sense, but to begin, R, the algebra RRA, is just Floer homology of L with itself. So L is this red thing. So, any questions?
Yeah, you started with a complex twofold.
Great, great.
I would have thought we would run some coherent correspondence because this is so far already.
Okay, okay. Everybody has some viewpoint. Yeah, yeah. Okay. Okay, so yeah, what happened? What is this? Great. So this one, so it was a, so when I say it's a mirror of the Kawamata Lagrangian, there is a slight lie, which is that it's not a mirror to, sorry, Kawamata vector bundle. It's not a mirror to Kawamata vector bundle, but it's a mirror to Kawamata vector bundle's restriction to the anti-canonical divisor, right? So first, that's the first correction. So we have this vector bundle on a complex twofold. It's a singular complex twofold. Inside this complex twofold, there is an anti-canonical divisor, which is this E, which is a curve. And this curve is, its mirror is twice punctuator, so that's some result that we proved. I mean, it's that's an old result. That's an old result. So there's a paper I wrote with Polchik in 2017 if you want a kind of souped up version of it, but it's an old result. So really, this L is a mirror of F restricted to E, okay? But why do I get this R then, right? So the R was endomorphism of F on the surface, right? But that's a little lemma. So if you have a vector bundle on a surface, if you restrict it to the anti-canonical divisor, you can chase through an exact sequence and show that home is isomorphism. Okay, so do you want to see that? Yeah, so I can do that very quickly. How are we doing in time? Yeah, okay. Because we still have to deform. We haven't come to the deformation stuff. So, but let me just quickly observe that that's a well-known lemma, which is the following. So in X bar, this is our surface. X bar is the compactified thing. We have this short exact sequence of sheaves. It's the anticanonical OX bar and OE. Okay, so E is the zero set of the section of the anticanonical bundle. Sorry, E I wrote it like this, I guess. Okay, and if I tensor this with home FF, so F is our vector bundle. What happens is we get this long exact sequence. So it's on the surface, and then this is in the restriction. And then there's one more term that I need to write, x1 f tensor omega x. But the claim is that this and this vanishes by Serre duality. So this is x2 of ff, so it's 0. And this is x1 of ff, which is 0 for the Kawamata bundle, right? So I told you it's a bundle whose x1 and x2 vanishes. Therefore, home ff is isomorphic to home restriction. It's the same thing as like when you have Lefschetz vibration on the A side and the timbals can restrict to the fiber. It's isomorphism. So same thing. When you have a Fukaya-Seidel category with timbals, the home of the timbals, you can compute it in the fiber. You restrict it. Huh? Yeah. Why not? The same timbal is just an exceptional collection. Yeah. Home, degree 0. Degree 0. Home is degree 0. I didn't claim x1 is 0 here. Okay? So it's not isomorphic. So home is degree 0. Okay? Yeah. So it's clear that this guy doesn't have x1s. Yeah. So only home. But that's all I care about. Right? So this is RRA, and this is RRA. Right? So therefore, I can compute it after I restrict. Right? But then when I restrict, I know how to do mirror symmetry. So I can mirror just that curve rather than the twofold, and then it becomes this curve. Okay? And now here I can compute stuff. So just the degree 0 part. Okay? So the intersections give me basis. There is an identity as well. And then there is this disk. So like this. Okay? And that's the products of the Kalck-Karmazyn algebra. So all that, that grid that I say, it comes from the triangles in this picture. Okay? So that's the universal cover of this picture. Okay?
It's still somewhat funny. I mean, on the B side, the only reason you got an elliptic curve is that you did this computation. I guess on the A side, it's the same. You did some kind of computation.
Yeah, on the A side, I didn't bother to think about the mirror of X bar. You can't think about that. But the point is this algebra can be computed in this one-dimensional thing. So, and then this is what we call now Kawamata Lagrangian. It's the mirror to the restriction. Okay.
So you don't know the mirror of X bar.
Yeah, I mean, you can probably, first of all, X bar, we are a bit agnostic what X bar is. Right? X bar is some compactification. There's lots of them. So you can pick one and then try to find a mirror to that. You can do that.
So how did you come up with that picture?
Oh, how did I find the mirror? Yeah, good. So, right. So.
Okay, let me try to guess first. So you do duality construction. So how, because like, so for example, you know this Stroke construction, right?
No, there's no such things. Yeah. Right. So now we come to your Hirzebruch-Jung. So your resolution story. So X bar RA, right? It's the singular one, and it has a resolution X tilde RA, right? And that is, so this is a projective surface with singularity, right? So it's kind of like something like this, singularity. And this singular point gets resolved by blowing up. And you blow it up, and then you get some picture like this. So these are, except because this is a cyclic singularity, it is just a bunch of P1s. And each P1 has some self-intersection, so it's like gamma 1. So these are, there's k of them for some k, and each of them has some self-intersection, minus A1, minus A2, and so on. And that's the Hirzebruch-Young continued fractions of R over A, not R over R minus A this time. So R over A, okay? So that's a very classical story, and that's why Hirzebruch has his name in this. So you resolve the cyclic singularity by blowing up, and then there's this exceptional divisors, and their self-intersections are computed via this way, okay? K. What? So, yeah, okay. So, and then there is a description of the Kawamata. Remember Kawamata bundle, Kawamata constructed over here, right? But there is a description of it in terms of this one. And it says follows. So that's a paper of Karmazyn, Kuznetsov, and Schindler. Okay, so what they say is the following. So this is a smooth surface. Now in this smooth surface, there is the following line bundles: L0, L1, LK. Okay. So this is a gamma 0 is this what I called as A before. So it's these curves, and they define now everything is smooth, right? So these are just line bundles. You take these line bundles, and then these line bundles they are except gamma 1 is this first one. Okay? So these are gamma 1, gamma 2, gamma 3, up to gamma k. Okay? So they are just the exceptional curves, and then gamma 0 is the first one. These line bundles. Yeah, well, sort of, but they're like you take the sum, right? It's not. Yeah, but you take the sum in order for it to be the second guy and not the first. Something so like that. Right, so, something like that, yeah. So this is an exceptional collection. Exceptional collection of line bundles. Okay, so this was, these line bundles are studied very well. You just, this is a smooth surface now. So, in here today, our focus is the category of singular thing, right? The category of smooth thing is a much more studied thing. So there's lots of papers about this. So, and then the point is these guys are an exceptional collection. So, and what they proved is if you take this exceptional collection and apply our algorithm, so self-extend them as much as you can, you get a vector bundle here, and that vector bundle is descends to the singular one. Okay, so and that's the Kawamata bundle. So
you have this L0 to LK like that.
Yeah.
What do you mean by apply the same algorithm?
So it's a collection, right? You self-extend them. So if there's an X1, you add it, and then you get a new object.
So yeah. Large L1, and then large L2, or
so yeah, in the end, it becomes something like this. So LK, LK RK. So it's some complex. It becomes K0. Sorry, K Did I call it K? Yeah, I don't know. So KR. So it's some twisted complex like this. Okay, so these are exceptional. So there's only homes from LK to Li to Lj where I is greater than j. Okay, if there is an x1, you extend them by putting that. Okay, you get a new object, and then if you can extend more, you extend it more and more, iterated way. So just like the previous discussion, just apply to the union of the direct sum of them.
Okay, so you build a chain complex of this form.
Yeah, you build a complex such that in the end there is no extensions with these guys anymore. Okay, so this is what you might call F tilde, and they show that this F tilde is a vector bundle here, which is a pullback of a vector bundle here. Okay, but the point is, like, how did we come up with that one? It's very easy to find the mirrors to these LIs when you restrict to the anticanonical here. Anticanonical here is the same, A and B, but also these chains now, right? So, yeah, so A, B, and then there's this gamma i's now, right? The mirror to this one is many punctured torus now. It's not just two punctured, it's a many punctured. The number of punctures is the same as the number of nodes. Okay. Okay. But mirroring Li is very easy because Li is just a line bundle and it's determined on this curve. What it is determined by the degree on each P1. Okay. So, and from this, these self-intersections and so on, you can compute their degrees. So they become very simple. LIs become very simple line bundles here. So they become very simple curves here. Okay. And then to those curves, we apply this construction. And then output of that is that curve, but inside this many puncture thing, right? But what happens is, sorry. Yeah, it has however many nodes you have. Yeah, the number of nodes, including this one. However many nodes you have is the number of punctures. But each Li is very easy to mirror because they're just line bundles on this curve. So, and then this complex, we can do it. So we draw lots of very simple curves, and then we do this complex in this torus, and as a result, we get that one. Okay, so let me draw an example maybe.
I mean, nothing depends on the choice of complex. Suppose I didn't compactify. Should there have been a computation that worked without compactifying? Is compactification crucial for that? So this way?
It is, yeah. So for example, this Sarduality business would not work. That's one. The restriction to the anticanonical would not be, home spaces would not be isomorphic.
Oh.
Right. So, yeah, it is important. But it is important and not important at the same time because the resulting object is independent of the compactification, but you have to work with one compactification.
So I didn't understand. I thought the first part, the guidance in the first place of your SOD was generated by computer machines, not by versal. And now you're producing the versal.
That's right, because it's the dual guy.
Because it's dual.
It's the dual to the generator, yeah. It's because I want to write it as a Dirac-Deleuze finite-dimensional algebra. Yeah. So, yeah, let me just quickly give an example, a precise example. So let's do 114. So in that case, the resolution is like this. So this is a -4 curve. And gamma 0 is this one, and gamma 1 is this one, right? And the line bundles are L0 is O of minus gamma 0, and L1 is O of minus gamma 0 minus gamma 1, okay? And here are so the curve is 3 lines, right? It's a 3-punctured torus. 3-punctured torus is the mirror, okay? And here's how they look. L0 looks like this. This is L0. And L1 looks like this. So this is L0 and L1. looks like this. So it's okay. This is L1, and now we do the
So I follow that to have this exceptional, have this P1s inside the Kollár.
right. Yeah, this is the resolution of this 4-1,
Yes,
right?
Right.
And then I'm telling you the mirror to these line bundles, the restriction of these line bundles to this curve. Okay. So they have certain degree, and then that degree can be like basically how many times this winds around those holes. So it's very easy to figure out what they are. But the Kawamata bundle is the extension like this. Okay, so I have to take 3 copies of L0 and then extend L1 by that. So that you do like this. So you take 3 copies like this, okay, and then you resolve these ones like this. I think did I? Yeah, I think I did the wrong one. Sorry, I resolve these ones. Yeah, so let me do it again. Sorry, I should have just copied. So yeah, you resolve this one and this one, okay, and that's our Kawamata Lagrangian. And the point is, once I do this, these 2 holes come together, okay, and that 2 hole you can now collapse to just 1 hole, okay, and that's the statement that this Kawamata bundle here descends to the Kawamata bundle here because it has degree 0 here. So you do this construction such that these 2 holes can be merged together, and when you merge them, you get a twice punctured one with that Lagrangian corresponding. Yeah. Okay. Okay. So now I want to go to the last part of the talk, which is the deformation. So how much? Okay, because I think I'm gonna run out of people are gonna run out of patience. Can talk more. So okay. So the next last topic. Okay. So this is the kind of the. If you want to remember anything from this talk, this is the main discovery. Okay. This Lagrangian.
If A was R minus 1, you would just get the.
Yeah, that's the AN case. Yeah. And then the Lagrangian looks very simple. That looks like this. So somehow it doesn't go around the torus. It just stays in the cylinder. So it's kind of like this. Right. So this kind of thing is the case of the AN. Yeah. Yeah. Okay. And then another thing maybe I can say is that in that case, it does. And in that case, the finite-dimensional algebra is kx modulo x to the n. Okay, so that's AN case gives you this one. So there's actually 2 special cases where the algebra is simple. So R A can be R minus 1. So that's the AN singularity. And then in that case, we get kx modulo x to the R minus 1. Sorry. So I should have an R dimensional algebra. Is this the right one? Yeah, this is the right one, right? So whenever you have AN, you have this n plus 1 or n minus 1. So, and then the other one is R comma 1. And in that case, we also have a very simple algebra. So it's still, it's also commutative. But it's a fat point. Okay, so it's these are the only cases where this finite-dimensional algebra is commutative. Okay, so one of them is this truncated polynomial algebra. The other one is the fat point. Okay. What do you mean? How do you understand? It's just the ideal square. Like all possible products is 0. Yeah. Huh? So yeah, if I didn't put 2 here, it will be just a point, right? And this is square. So those are the only cases that you get commutative algebra. Otherwise, it's a finite-dimensional non-commutative algebra.
So you have a simple construction somehow deduced them, but you derived.
What do you mean?
Well, you said that if these are the line bundles, they have to mirror that, but it's not like it's not some first principle thing, right? You said basically because I know the line bundles, it can be nothing else.
No, it's a theorem. Yeah, I mean, we know mirror symmetry for this sufficiently well that I can tell you what line bundle goes to which curve exactly, and then I couldn't tell you immediately where this vector bundle goes to because it's a complicated object. But the line bundles I can easily tell from the proof of the mirror symmetry. So they go to this particular curves,
so
and then
because you understand mirror symmetry for the curve so well.
Yeah, so I can mirror the line bundles, and then this complex I can do it here, and that's the mirror to F, right? So now, so far, it's nice. We have mirror symmetry pictures and so on, but we didn't teach anything to algebraic geometers, okay? Because they could compute this algebra already. So, but now we will teach something. So that's the next thing. So, which is the deformation. Now that I have this thing here, I can compute everything about it, and algebraic geometers cannot compute some of them. So here's the next. Yeah, to be honest, my collaborator is an algebraic geometer. So, did I say his name?
I guess it didn't.
Yeah, why is this happening to me? Yeah, so my collaborator is Jenia Tevelev. Okay, so yeah, I learned most of the background from him who studied this stuff. So in algebraic geometry, but now there's a new viewpoint. So now here's the idea. So we saw that's the preparation for this was this the two P1s intersecting, and then we smoothed them, right? We got this order. That was the simple case of curves. Now we'll do the same thing here. Okay, so we have this X bar. It's a singular surface, and this singular surface will be at 0. Yes, and then we'll deform this to a threefold. Okay, so this is going to be a threefold now. Okay, or maybe more fold. It depends on the dimension of the base of the deformation, but let's do threefold. Okay, so let's call this KT, and this is X fibers over KT. XT will be smooth surface for T not equal to 0, and X0 is X bar. Okay, so there is a very beautiful theory of smoothings of cyclic singularities. So maybe I should keep this. So when you have an AN singularity, you know this very well. There's the AN Miller fiber. So it's a hypersurface, right? It's a zero set of some function, and then you smooth it. It's the you know at 1 you get this. Symplectically, it will be a plumbing of T star S2s. So it's kind of some smooth. Well, I skipped a little bit. Yeah, I kind of was talking about affine story, but anyway. So when it's a cyclic singularity, more general cyclic singularity, there is something interesting happening, which is there are different deformation components. Okay, so this was completely described. Well, not completely, but to a large extent, let's say, described by Kollár and Shepherd-Barron. So this is a 1988 Invenciones paper. It's a very important paper. So it's one of the most cited papers in minimal model program. And in particular, it has the story that Fx, so X is the affine cyclic singularity, right? So X is just this C2. So let me just use this 1AR, right? Has irreducible components indexed by P resolutions. So this is a, let me tell you slowly what this is. So we have a, so let's do first the first non-trivial example, 1 over 4. Okay, so this is a famous example. This example is a you take the quartic curve, you know, so something like so. This is a P1 in whichever how many 1, 2, 3, 4, 5. So it's in P4, right? And then you take the cone over this curve. So it's a P1 embedded into P4, and then you take the cone. Okay, so that's so this is this singularity. Okay? So that singularity has two deformations. Okay, so the two different deformations. So one is, and so this def x is the space, the base space of deformations. It looks like this. So there one is one-dimensional, the other one is three-dimensional. Okay, so this is A3, this is A1. So this is where the singular guy is. You can go along this A1 and you get some smoothing, or you can go here and you get some other smoothing. Okay, so it's very different than AN singularity where there's only one component. Okay, and it's very nice. There's a very nice description of this. So we can describe this singularity in coordinates as follows. So we have x5, and this singularity is described by the following: x1 to x4, x2 to x5. The rank of this matrix is less than or equal to 1. So that's another way of describing the affine part of the singularity. Okay, so it's you have some equations here. It's several equations, right? The minors of this matrix has to vanish. That's describing this singularity. Okay. Now, how do you smooth it? You smooth it by looking at the following. You look at rank x1, x2, x3, x4, but you change these guys to x3 plus t1, x4 plus t2, x5 plus t3. And then you do rank of this less than 1. So that's this component, t1, t2, t3. Okay. So that's a 3-parameter family of surfaces. At 0 is our singularity, otherwise it's smooth. Okay. What about the other component? The other component is you write it like this. So the same equations can be written as rank of the following matrices. X3, x5 less than or equal to 1. So it turns out this, and this gives you the same equations. And then you can put an S here. And that gives you this other component. Okay? These components do not talk to each other. They intersect. You look very... Huh? Okay. So yeah, so these are these different components. That's a convenient way of writing the equations of this singularity. Okay? So it's a bunch of equations, this singularity, right? And it's not a hypersurface, right? So it's just a bunch of equations. And here's a convenient way to write these equations. You just look at the matrices, so this matrix, and you look at all the 2x2 minors vanish. That's the equations of this singularity. So it turns out it's also describable this way. So, so that's just say that there's two components, okay? And so in general, when you have an RA, it's very complicated, the number of components that you have. So it could be really complicated. And these guys gave a combinatorial description of how many components are there and what are their dimensions and so on. Okay. So, and what we can do is we can take our x bar with our vector bundle and go along deform along these directions. and see what happens to the algebra. Okay, and that's what we computed for using this picture. Okay, and the way you compute it is, so remember, we were on this picture, these points, they give two generators for your inverse homology. The degree 0 part is these guys, but they also have degree 1. Okay, and those degree 1 elements you can use as bulk terms. So you can count.
Here, the strands.
You need to draw another Lagrangian curve, right?
Huh?
You need to draw another Lagrangian curve.
Yeah, you can see it that way, but I mean, it's simple enough that you can just say, like, there's two generators here. One is, zeros are, if this is input 0, this is an input 1. Yeah, it depends on from which corner you get in and which input and which output. Yeah, there's inverse homology.
So I guess the question is like, here you're drawing a single Lagrangian, inverse Lagrangian.
Yeah.
However, the things on the left edge more than the things on the right edge.
That's not true. They have to be equal. Did I draw wrong? There's 7 here and 7 here. It's just a single Lagrangian. This is an irreducible Lagrangian. It's an embedding of S1. Sorry, it's an immersion of S1. It's just a complicated immersion. Yeah. Okay, so, but the point is,
the algebra of this side is not in degree 1, in single degree, right?
so this one is in degree 0, but there's also HF1, okay? And
so that one, per definition, the 0 component, the degree 0 component of the actual algebra. Right?
This actual algebra is the degree 0 component. And what I'm saying is there's X1 classes, right? And I can try to use those X1 classes to deform this algebra. Huh?
I thought it's like an artifact.
Yeah, I agree. It was an artifact, right? But so, this X1 class does not exist upstairs. That's true, right? But what happens is when I restrict, I can now deform the algebra using the X1 classes. So, and that concretely corresponds to, instead of counting triangles, right, I also should count rectangles, where one of these is an X1 class, HF1 class. So this is the element of X1.
Okay. So you deform the algebra by deforming the object L. So that.
Right, so that's right. Yeah, I deformed the object L. Yeah, that's right. Right. But there is an explanation for this that it might make sense, and it's hidden in this picture. So remember, in here, we had this curve, right? This E in X bar. And I restrict the bundle to this E, right? But now I deform it. This guy also gets deformed, right, along with it. And what happens is it becomes this one. So this corner gets smoothed. So it's a family of E's, right? So that's so we can try to play the same game with this deformed bundle, restrict to these guys, right? And but we have mirror symmetry for a family of elliptic curves too. It's the relative Fukaya category. And remember, I only smooth one of them. So it's actually you only put here. So you use the relative Fukaya category where you count intersections with this one. So, but the interesting thing is the following. If you just compute the endomorphism algebra of this Lagrangian in the relative category, paying attention to this S, so that means you count more triangles, right, possibly passing through here. That doesn't give you a flat deformation of the endomorphism algebra, so the rank drops. So what you need to do is you need to deform. You fill in this hole, you allow holomorphic curves, but you also allow some bulk terms.
You have to put in a bulk curve to make it
such that the cohomology doesn't drop rank. So that's the yeah. So let me just try to say that. So we're going to compute HF L, but inside FT1 D, right? So relative category with respect to this D, but not L, but L equipped with a X1 class. So it's called a bounding cochain. Okay, in such a way that this family of algebras, now this family of algebras, there's parameter here and there's parameter here, right? The rank of HF0 is constant. I want the rank to be constant so that it's a flat deformation of algebras, right? So, and for that, there's interesting equations between this B and this divisor parameter, and those different equations correspond to these different deformation components. So, so for this one, for example, yeah, maybe let me just. I think I have to slowly stop, but let me just tell you what it boils down to. So this 114 case, right? It was the Lagrangian is something like this. Okay. So now I filled in this hole. In order to go along this direction, okay, this component, what I do is, as I fill on this hole, I also put a bounding cochain in this point. Okay. So that means I count rectangles whose corners can be in this B, but also passes through this S. And those satisfy an equation. If I want to go here, then I have the same Lagrangian. Okay, I again fill this hole, but now I put bounding cochains in here. Okay, and those satisfy an equation. That equation allows me to go here. That's true. So it's this picture is so we didn't. So remember, I'm paying attention to the E. So I don't just deform X, but I deform E together with X. If I do that, it becomes A2 here. It becomes A2. So, but there's a one-to-one correspondence between the components. Yeah. So to finish, the final game is the final interesting thing is there is deformations of this algebra HF0. It can be explicitly computed. We computed it, so it's a very, very involved rectangles, and it has to be done component wise, right? So somehow you get you require that this algebra has finite is flat, so the dimension of this is constant. So that requires choosing a bunch of these intersection points and solving the Morar-Cartan equation. Different Morar-Cartan solutions correspond to the classical story of, that's a conjecture. We checked it up to R equals to 32 or something. So the Kollár Shepherd-Barron description of possible cyclic, possible smoothing components is isomorphic. So I haven't finished the statement yet. So is in bijection with possible deformations of this this endomorphism algebra by putting bounding cochains. Okay. That's right. And we checked it until R equals to 30 because we have a combinatorial formula. You just enter it to the computer and then it can check it. But it's not clear why this is true. It's not clear. And the components, the number of components can be arbitrarily high as RNA changes. Yeah, different. It's very complicated. Yeah. Okay. All right, is that okay?
Thanks, Yanki, for this
yeah.
wonderful show. Yes.
Yeah.